Okay, we'll go ahead and start. Thank you all for joining us this afternoon. My name is John Mankowski. I'm the coordinator for the North Pacific LCC, and it's our pleasure today to sponsor this science management webinar. This is a 1-hour webinar via the phone connection and also over the WebEx. We sponsor these webinars periodically when key products from the research that we and our partners fund become available. And you're going to hear a great presentation today regarding the effects of climate change on montane wetlands that's presented by Maureen Ryan. So before we kick it off, I just want to say a couple of things. One is this is an NPLCC-sponsored science management webinar. We host these periodically. If you haven't already, please go to our website and sign yourself up to join our listserv so you can receive announcements about RFPs or future science webinars. And also regarding the products and the final reports. If you're looking at your screen right now, you can click on our Projects and Resources tab, and then click our Projects button at the top. Then look at the projects funded by year. This one was funded in 2011. If you click on that, you'll be able to look at the titles. This, of course, was Hamlet was the PI. If you click where I just did, and then you'll see a description of the project. And then right down here, Access Project-Specific Proposal will get you to the project description, the final reports, and other products as they're available from this presentation and from others. So with that quick introduction to our website and how to reach the final products, we will go ahead and begin this webinar. Thank you, Maureen, for joining us. This project is focused on looking at hydrologic projections and how they affect montane wetlands in Washington, Oregon, Northern California. Its management relevance is connected in that many of you, scientists and managers, care about montane wetlands, manage species and habitats. And a current question we often hear, and the reason we funded this project, is there's some concern about how these often snowmelt-dependent wetlands are going to fare over time with climate change projections. In other words, these sensitive wetlands are wet now, but over time are they going to remain wet, and what do we need to think about in terms of managing them for species and habitats? Without any further delay, I'd like to introduce Dr. Maureen Ryan, who has a BA in English from Georgetown, a PhD in population biology from UC Davis. She's currently a Smith Fellow, sharing her time between UW and Simon Fraser University. Mo is an evolutionary ecologist and conservation biologist who's sometimes found in Bellingham, but usually crossing the border and working on her science. I am going to now pass the controls over to Maureen. And Maureen, you will run the presentation from there. The way we'd like to handle questions on this is after Maureen is done presenting, you're welcome to just unmute your phone and throw your questions out there. If it becomes too disorganized, we may ask you to send your questions in over the webinar. But right now, I think we're going to be just fine, and I'm going to pass it to Maureen and let you take over. Maureen, thank you.
Great. Thanks, John, for that introduction, and thanks all of you for calling in today. I'm getting a little bit of feedback from somebody. I'll just make sure that your phones are muted. That's fantastic. So, yeah, thanks for being here. I'm really excited about the work that we've been doing on wetlands in the Pacific Northwest. And this project was, a lot of the initial funding came from the North Pacific LCC, so we're hugely appreciative of them for getting us sort of off the ground. So I'd like to start just by introducing some of my colleagues in this work. This has been a big collaborative project, and a lot of the work I'm showing you today was developed by my close collaborators. So Alan Hamlet and Sayun Lee, who developed the hydrologic models, Megan Halifisky, who has done all of our wetlands mapping and remote sensing, and then Wendy Palin, Mike Adams, and my fantastic field crew of Noel Steinweg, Reed McIntyre, Ray Parks, and Merrick collaborating on the field biology and the ecological application. So I'm still getting quite a bit of noise from somebody, so I'm wondering if you could just check your phones one more time. Thanks. Okay, so talking about wetlands and climate change.
Maureen, let me interrupt you. Are you sharing your screen yet?
I am. Can you not see it?
I'm not seeing it. Are others seeing Maureen's screen?
No.
No. Okay. Oh, sorry about that. Let me try again. Can you see it now?
That's working, yeah.
Yeah.
Okay, fantastic. Sorry about that. So here's some of the people I was talking about. Yeah, so
Somebody still has like a cell phone. They need to put it on mute because I'm hearing feedback like somebody's in the kitchen or something.
Yeah. Okay, well, I'm going to start. I'm still hearing quite a bit, so maybe I'll make one last request for folks to check their phones, and I'll just continue. So our group is really interested in obviously working on wetlands and climate change. And wetlands are one of those ecosystems really widely cited as being essential ecosystems for a lot of different, ecological processes and for wildlife and for a variety of ecosystem services. But, because they're somewhat complex and because they're often integrated into other kinds of ecosystem types, they've historically been somewhat understudied and under-resourced. And so, our interest in working on wetlands came partly from that and also just from them being really fascinating ecosystems. So a lot of what, our group is responding to, oh dear, let's see, there we go, are these calls that have come out of both international and national agencies and bodies, really recognizing that we don't know enough about wetlands, and so we have sort of limited ability to, in particular, project the effects of climate change on wetlands. And there have been these repeating calls for study and resources to address that, repeating throughout the different IPCC reports, through organizations like Ramsar, and then also within the U.S., a lot of the federal agencies really in their climate change reports asking for particularly resources to help manage and understand the effects of climate change on aquatic ecosystems. And so this was motivating for us, and it's really the work that we're trying to address. So our goal is, we call ourselves the Wetlands Adaptation Group, and our mission is really to develop resources to enhance science and conservation of wetlands in the face of climate change. And of course, this lines up really nicely with the North Pacific LCC's mission of developing, coordinating, and disseminating science to inform landscape-level conservation and sustainable resource management in the face of climate change. So this was, early on a very natural partnership between the two of us. So as an overview of what, kind of the challenges that we see in addressing wetlands and climate change, again, these, they're unique systems. They're very diverse. Wetlands, there's no such thing as a single kind of wetland. They're very diverse. They're across all of these ecosystems, and they have some unique challenges as a result. So I'm just going to kind of run through those as framing for the talk. The first of these is that, for one, wetlands are made of water, so they're naturally very dynamic. They're very responsive to precipitation and temperature kinds of changes that we expect to see with climate change. And so the kind of null expectation has been that wetlands are likely to be very sensitive to climate change, and particularly montane wetlands that are in these regions where we are already seeing in some cases, especially in the Northwest, and then expecting to see further changes in the distribution of snowpack and other really important hydrologic drivers. So that's kind of the core issue. Wetlands are also incredibly, they're incredibly changeable. So, for example, this is one of our sites from the Olympics that in the summer is this tiny little pothole, but, over the course of even just a few days of heavy rain can turn into something that's much more expansive and connected to ecological processes associated with that or more. Another really fundamental challenge that we face in thinking about wetlands and climate change is the fact that we often don't know where they are. It seems like kind of a basic tenet. In order to study something, you need to know where it is in space, and that's actually not always the case with wetlands. So, for example, these are some of the sites, some of our core field sites in the Olympic Peninsula, and this is up in a 7-lake basin. And so you can see from aerial images that this aggregation of ponds, but if you were to look at the USGS water layers, or something like the National Wetlands Inventory, a lot of these ponds don't show up on maps, even though they're actually ecologically important. So one of the core issues that we face, where are they, and how do we know that we're assessing the right things based on good information? I'll talk about this more in a few minutes, but this is just an example of where we're challenged by this as well, with some of the older maps being either wrong or incomplete and really underestimating the distribution. So that's another core problem. The third challenge is that they're understudied. They tend to be very diverse, so very different processes are regulating different kinds of wetlands, and there's usually pretty limited baseline data. And for all of those reasons, brings us to kind of the fourth challenge, which is that we have limited ability to forecast ecological effects of climate change because of all the prior reasons that I mentioned, and as a result, limited ability to manage for climate change. So
Let me jump in real quick if I can, Maureen, and just remind everyone to please place your phones on mute. There's someone that's jostling their phone in their pocket or something that's causing some annoying background noise.
Thanks, John. So those are the challenges that we face, and stemming from that, these are the questions that we really set out to address through our research. And they're pretty basic. Where are the wetlands? What are their dynamics? Which wetland types are most at risk under climate change? Where are the hotspots of risk in space? And our options for conservation action in the face of those challenges. So just to kind of bring you into the reality of what these places look like, I wanted to show you some photos of the kinds of sites that we're focused on. So these are montane regions of the Cascade and Olympic Mountains. This is a site, for example, called the Potholes in Olympic National Park. Really beautiful, very ecologically rich area. Some other sites in the Seven Lakes Basin, Mount Rainier. This is another shot from the Olympics. And then also in the Cascades. So, very different kinds of wetlands across these two very different ranges. And we really focused on a few wetland types as a start that we hope to expand on eventually. But as the first round of this project, we focused on these 4 wetland types. And we categorized them as short hydro periods. So these are the little pothole ponds that are snowmelt fed and dry up really quickly after the snow goes away. Intermediate hydro period wetlands. And these are some that they may or may not dry every year, but if they dry, it's late in the season, so ecologically they can still support things like fast-developing frogs or invertebrates that have an annual life cycle, or at least annual larvae. And then perennial wetlands are those that rarely or never dry, but often lose a significant portion of their volume. And permanent wetlands that generally don't dry at least over a kind of, century-long time scale, and they don't tend to lose much of their volume either throughout the year. So those are kind of the 4 classes, and there are a lot of different, it's worth mentioning, there are just a lot of different ways of classifying wetlands. This is really based on hydrologic classes that can be related to a lot of the existing classification schemes like the Cobarden or the HDM and other forms of wetland classification, because they're really focused on those hydrologic drivers. Our group is working in a variety of regions, and I'm going to focus on those that are within the NPLCC boundaries, so the 3 national parks in Washington State. But I wanted, just in case some of you are working outside of that, to mention that we're also basically doing the same thing in the Columbia Plateau, in Douglas County and around the Swanson Lake. So just as a review of the projections for the Pacific Northwest, looking forward, most climate models have strong consensus around a projection of strong warming in all seasons, especially in the summer, and relatively small changes in annual precipitation, but the distribution of that precipitation is expected to change pretty significantly. So in particular, we expect to see wetter falls, winters and springs, and drier summers, and this is both due to changes in the timing of precipitation and also the form as we see shifts from snow to rain. So, of course, thinking about montane hydrology and ecology, the biggest thing that we're concerned about is this transition from snow to rain. So what we're looking at here is a map of watersheds in Washington State, and the blue watersheds are those that are currently or projected to be dominated by snow. The red are these transitional watersheds that have, over the course of the winter, snow on rain events, and then rain dominated at the lower elevations. So what you can see in this image is that, currently we have quite a bit of the Cascade Range is considered snow dominant, but over the next 70 years, across both climate scenarios that are represented here, you see this complete loss of the snow-dominated watersheds and then a transition to both more transitional watersheds and also an increase in the number of rain-dominated watersheds. If we look at that a little bit more closely, what we're looking at here are hydrographs of those three different types of watersheds. So with rain-dominated, of course, you can see that most of the water is moving through the system at the time that it's falling. In contrast, in the snow-dominant watershed, most of that rain is most of that precipitation is being held, of course, in reserve in the snowpack, and then as it melts, is slowly percolating out with a peak of water flows during the summer. The area that is most of concern are these transitional regions where the hydrograph changes really radically. So all the different colored lines are for different climate projections. So the black line is the historical, red line is the 2080s, green is the 2040s, and blue is the 2020s. So what you see is this gradual shift in these transitional regions from a hydrograph that looks a lot like a snow-dominated landscape to one that looks a lot like a rain-dominated landscape. And that's a huge, ecologically that has huge differences in terms of water availability for different species. So overall, the concern is that changes in precipitation and temperature are going to lead to changes in the availability of wetland and pond habitats and in the timing of inundation and drying that's important for the life cycles of the organisms that use them. So if we come back to those questions, that's kind of the climate backdrop of thinking about each of these issues. So I want to show you what we're doing on each of these questions and some of the products that are coming out of our research that I hope will be of use. So the first is this question of where are the wetlands? And I come back to this map that I showed a little bit earlier. What we're looking at here is an aerial photo of some sites in Rainier National Park. The bluish-green areas are wetlands that we've mapped through some methods that I'll talk about in a moment. The red polygons are the NWI, the National Wetland Inventory, which in its time was using the technology that was available at the time it was developed was the best that we could do of mapping wetlands based on aerial imagery. The technology has changed a lot since then, and so a lot of those maps are currently out of date. They have offset errors that you can see represented here where the polygons are actually shifted a bit away from the wetland itself. But the biggest issue, especially for thinking about montane wetlands, is that they have really high errors of omission. So we're just missing a lot of the wetlands that are there, and that makes it hard then to evaluate what might happen to them or their ecological relevance. So that's again, the issue that we're facing. So a woman named Megan Halabitsky, who's a PhD student at University of Washington, is a key member of our team, has been developing these new ways of improving and updating wetland maps based on something called object-based image analysis that uses high-resolution aerial images and computer algorithms to identify and recognize wetlands. So I won't go into too much detail on the methods. I'd be happy to talk to you afterwards or point to Megan on this, but the key point is just that this process automates recognition of certain features in the landscape. You train the computer through an algorithm in a program called eCognition to pick out certain features in the landscape. It's really flexible. You can use all kinds of different available databases, so it's more flexible and more capable of picking out both very small wetlands and also wetlands that might be missed by some of the more traditional practices. And so just to give you a sense of what this looks like, if you take, for example, an aerial image of the same region in Mount Rainier, the program will segment the landscape according to its spectral characteristics. You then train it through an algorithm to recognize certain features. So in this case, we're pulling out open water and emergent vegetation. And then that essentially gives you a map of those features. And this can be extended across whole landscapes. It can be used, like what we're doing, to make it even more sophisticated, to classify certain wetland types based on their distribution in the landscape, certain features. And so we can come up with these very fine-scale maps that have the wetlands identified and classified. You can add other features of interest like trails. And then this can be extended across, across the whole land. So we're running this basically for all 3 of the national parks. This is another region of Mount Rainier. We have to mask out some areas based on their topography. They're either too steep or the errors are too high because of shadows and really intensely vegetated places. But the core point here is just that these maps give us an ability to pick up wetlands that aren't on any other maps, and so we have much better ability to actually evaluate what's at risk and which types of wetlands are at risk across these large spatial extents. So those are some of the products that are coming out of this part of the project, are these updated maps in the regions that I mentioned, and then also remote sensing algorithms, so the training programs for e-cognition extended to other areas with similar topography outside of the park, wilderness areas, national forest areas, places like that, that can be run even if it's not one of our focal regions. So, so that's getting at the question of where are the wetlands, and then to look at what their dynamics are. We have a few different approaches for that. So this obviously isn't in the mountains, but to give a sense of, we all know that wetlands change fairly dramatically from year to year in some cases, and we wanted to be able to quantify that better and understand its implications. So we've started a field monitoring program in our focal sites. We have 3 core sets of sites in each of the national parks where we're actually collecting hydrologic data, both by physical monitoring and also by using these things called I-buttons, which are temperature data sensors, data loggers, being conspicuous, so we can put them out in places that have a lot of visitation without them being disturbed. And they basically indicate when the pond has dropped a certain level. So using the signal of temperature variation, we can tell whether the pond dried or how far it dropped by putting these transects of I-buttons out in the field. And so that's another way of collecting more data and also reducing the amount of statistics that we need to make to each site. The final, or the third, I should say, way that we're trying to collect more data on wetland dynamics. Right now we're only doing in the Columbia Plateau, so I'm just going to mention it quickly. But this is an extension of the work that Megan has done on mapping, where she classifies a pond using object-based methods, and then uses Landsat imagery, which has a frequency of imagery every 2 weeks. So you can basically overlay that polygon of the pond on top of the Landsat image, and then use another approach to evaluate how much water is in the Landsat pixels within that area. And so what this gives her the ability to do is actually reconstruct wetland hydrology going back for the 25 years that Landsat imagery is available. And so those are data that would otherwise be lost in time. And she's able to generate figures like this one. This is just an example from one pond that shows the wetland dynamics of this particular site for each year over a 25-year period. So, we can see how that wetland has varied in its hydrology, and you can also see that it's kind of gradually dried up over time. So this is the kind of thing that we're not currently doing yet for montane areas because the cloud cover is an issue, but it's something that we're trying to develop and have developed in other regions that allow us to get at some of that historical hydrology and also use that to drive some of the climate models that are reliant on empirical data. And I just have a note here on the big simulations that there's another way of using this that I'll talk about when I get to that portion. So in terms of products that are available, we have data sets that we'll make publicly available if anyone has use for those on the dynamics of our focal sites in the 3 national parks. We're also collecting water temperature data We have reconstructed hydrographs for areas of the Columbia Plateau. And then the fourth resource, which I'll talk about in the next section, is another way of doing hydrologic reconstruction using the hydrologic model that we're also using to evaluate climate impacts. And I'll talk more about that in a moment. So those are some of the products that are going to be available. So then the next two questions are pretty closely related, which is, which wetland types are most at risk under climate change, and what are the hotspots of risk? And this is really the core of our NPLCC project and where we got started. So what we're using for that is something called the Variable Infiltration Capacity, or VIC hydrologic model. And the leads on this portion of the project are Faye and Lee, who's a postdoc at the University of Washington, and Alan Hamlet, who was at University of Washington, now at Notre Dame University. So the VIC model is it's a sophisticated, fully distributed, physically based hydrologic model. That just means that you need some empirical data to drive the model. It's implemented at 1/16th degree resolution, which means that the grid squares of its projections are about 5 by 6 kilometers square. And what the VIC does is it simulates soil moisture and other water balance variables, things like runoff, across these 3 different soil layers that represent about the first 1.5 meters of the ground. And so it's not a groundwater model, but it's modeling how water is moving both quickly and more slowly through those different soil layers. And the VIC can be run both looking at historical hydrologic patterns, and also can be linked up with climate simulations, climate projections to look at impacts moving forward. So that's why we're using it. The greatest thing about the VIC is that it produces hydrologic projections at multiple scales. So one of the big issues with wetlands in particular is that many of them are very small. They can be very idiosyncratic at times. And so we really needed a method that could line up the scales of variability that we see in the natural world at those sites with the scale of climate data that's available. So there's been this, this problem with a lot of climate projections and climate modeling of those things not really lining up. And so the VIC is kind of uniquely useful for that. What it does is it allows us to get very detailed projections of individual sites for which we have some basic empirical data on wetland dynamics. And then it also allows us to project over these much larger regions to get a sense of where are those hotspots of risk, what are the places that are likely to be most affected overall. And it allows us to simulate backward 91 years and also forward to 2080. So we can, when I was mentioning that other form of reconstruction, we can actually, based on a few years of empirical data, we can simulate what likely happened in that pond over the last 90 years. That gives us some indication of its historical pattern. And then we can simulate forward how that's likely to change under climate change. So it's quite a powerful model in that way. And I just want to walk you through what the steps are for using the VIC. So we go out, we're collecting empirical data. These pictures are from one of our sites in the Olympics that you can see is drying out over time. And what we do is we take those empirical data points, and then we look for the best predictors of that wetlands response and correlate that with different VIC outputs. So in our case, the one that has worked the best is soil moisture, which makes sense if you think about it. So what we're looking at here is simulated soil moisture from the VIC model is the red line, and then the X's are these, data points that we measured in the field. In this case, it's on volume. So we look for the best predictors. Soil moisture has worked the best. And then we generate regression models of that wetlands response. There's a model of the response. These are some examples from some of our sites in Mount Rainier and Olympic National Park. So, and for these 3 different pond types. What you can see is that they match pretty well. The correlations are often quite high. The models do a little bit better for sites in years where the drawdown of water is pretty gradual, and then it refills quickly. So that's the Rainier sites in this case. In The other case, Olympic National Park, the fit is a little bit less good because we missed in our monitoring some of the pulse rain events, but we still get a reasonably good correlation, 0.74 to 0.78. And so this just gives you a picture of what those regression models look like for different kinds. And so based on that, the key question, of course, with climate modeling, hydrologic modeling is, can we get the models to fit the historical wetland variability? And what we found was that we were able to do that with the VIC model. So the simulated soil moisture in the bottom soil layer was a really good predictor of the wetland drawdown, and the topsoil layer was a great predictor of refill. That kind of makes sense if you think about these ponds drawing down very slowly as they're drying up during the summer, and then there are these pulse rain events in the fall that refill them fairly quickly. Just a lot of it is just based on surface runoff. And so the good news is that our models based on regression relationships were able to reproduce that historical wetland variability, and so that gives us some confidence in our ability to model those changes going forward if we assume that the same physical processes are going to be at work under climate change. And so that's what the next step is forecasting that wetland response to climate change. So what we're looking at here is, for that same pond, the blue line is the historical pattern. So, for example, this is a year or a pond that dried late in the summer. If we look forward towards the 2080s, the projection would be for that pond to dry in midsummer, so about a month earlier, which is kind of in line with the changes that we would expect to see with drier, hotter summers and less rainfall. We can also look at the frequency of pond drying or other kinds of variables that have a more extended temporal signature. So for example, this is something that's really important for the species that I study, amphibians, where different species have different lengths of time that are required for development. So cascade frogs on the left need the water to stay in the pond long enough into the fall that their tadpoles are able to metamorphose. Something like long-toed salamanders that need multiple years of water because their larvae might take 2, 3, 4 years to develop and metamorphose into adults. And so these kinds of patterns are things that we expect to change and are concerned with. So, for example, in this site in the Olympics, the blue line shows that historically this is a pond that would have dried once every 5 years and therefore would have, for the most part, supported these two species. In the future, it would be expected to dry every year. And so that, at minimum, would knock out the long-toed salamanders, and depending on the timing of those drying events, should potentially impact frogs as well. So these are some of the ecological impacts that I'll be talking about a little bit more at the end of the talk, but this is how we're using the models to consider those processes. What we're also able to do, because of that 91 years of historical simulations and the ability to model forward to the 2080s, is that we can compare the frequency of drying for these different sites. And so we're able to forecast those differences. For example, this is a pond that historically would have dried 13 out of 91 years according to our historical simulations, 14% of the time, but in the future we'd expect to dry 85% of the time. So ecologically that's a big difference. And so we can do these kinds of things for the individual sites for which we have some basic empirical data. We can compare among regions. I'm showing you just 2 ponds here, but this is representative of the patterns that we've seen comparing, for example, between Mount Rainier and Olympic National Park, where the projections are for greater impact in Mount Rainier than in the Olympics. They're both trending in the same direction, but the magnitude of effect is different, and that's partly due to elevation and partly due to differences in historical snowpack and how that's likely to change in the future. Another thing that we can look at is the loss and transitions of particular wetland types. So just to explain this graphic a little bit, with those 4 different pond types that I mentioned at the beginning, short, intermediate, perennial, and permanent hydroperiod. Those are, you can kind of map those out in terms of how low they tend to, their average annual minimum, so and then how quickly do they change. With the at one extreme, the permanent ponds not dropping very low, not changing that fast, and the short hydroperiod ponds at the other extreme. So if this is a historical data set, we can look into the 2080s and see that a lot of those short and intermediate hydroperiod ponds go to zero every year. We're losing most of those habitats. And then if you look at this middle zone that, historically was characterized by these perennial sites that hold water in most years but don't completely dry up, but may drop a bit, you're seeing transitions of what were historically perennial ponds acting more like intermediate hydroperiod ponds, and likewise what were historically permanent ponds becoming more like perennial ponds. So this, of course, makes sense in terms of what we'd expect, but we can actually quantify some of those patterns in different regions. I think I'm hearing somebody's radio in the background. Thanks. And then the other, and probably what's more useful for most people who are, often not going to have that really fine-scale hydrologic data to look at patterns in individual ponds, is that we can aggregate the data that we have from all of our sites and then look at a coarser spatial scale, what are the hotspots of risk. So this is an example from a paper that we have in review right now. On the left is the historical pattern, and what we're looking at here is the probability of drying for those intermediate sites that I talked about earlier. And so you can see that there are a lot of regions, and they all basically along the crest and the high elevations of the mountains where there's very low probability of those types of ponds drying completely within each of those big grid cells. If you look at the 2080s, it's a very different pattern. And if you do the comparison between those two, the larger colored figure shows the change in the probability of drying. And so you can pick out those hotspots, or the red areas, are where we're expecting to see a really significant change in the hydrology of those sites and the loss of a lot of those intermediate wetlands, which we'd expect also to correlate with a change from.
Let me jump in for a second. There's some background music, like elevator type music, playing.
Somebody's put you on hold, and that's what's your background music. So that's what's happened.
This is it's kind of a meta presentation. Interesting background things happening. Thanks for your patience. At any rate, so what we're looking at here are, is something that we're hoping will be of use, to many people. Anyone who's interested in what's going on with wetlands in the mountains, you can look at these areas and say, what are the hotspots likely to be, and then can think about that in more detail in terms of like what kinds of wetlands are there and how are they most likely to be affected by these different drivers. So this is one of the other main products that are available. If we look at the patterns overall, I showed you examples from a few particular sites and for that core scale, but what we see across all the simulations is that climate change is likely to cause the earlier drawdown of ponds, a more rapid recession rate, so drying out faster, lower water levels, and then longer overall dry periods during the summer is pretty much what you would expect from the projections. And that these effects are likely to cause transitions in pond types, and that's going to mean the loss of some of those habitats that will affect different species to different degrees and are going to affect the vulnerability of wetland ecosystems and the species that depend on them in different ways across regions. So I gave you the one example of the comparison between Mount Rainier and Olympic National Park, but we could look more finely across the Northwest landscape and see those kinds of vulnerabilities are distributed unevenly in space. So a lot of the products that are coming out of this part of the work that are publicly available are these map spots and also projections of particular ponds. And for example, if any of you are out there and you actually have hydrologic data for wetlands, it's pretty easy for us to run these models and so we could run them and then generate much more detailed projections for anyone who's interested. The other thing about the VIC model and this approach is that it's applicable across a really wide region of the U.S. So we've focused on montane areas of the Pacific Northwest and mostly with Washington State. But the model's implemented, the VIC model that we use is implemented across the Pacific Northwest into Montana and up into D.C. And then there are other groups that have developed essentially the same kind of model across most of the U.S. And so these sorts of approaches can be applied much more broadly. We use the Northwest as a testing prototype, but there are further extensions of it. So that brings me to, what are our options for conservation action and how do these resources play into that? The way that I think about it is that we have the new maps tell us, where the wetlands are, projections of risk that can be overlaid on those maps so that we say, okay, within this grid cell with this level of risk, what are the habitats and how are they likely to be affected? We can line that up with ecological data where it's available and use all of those to plug into structured climate change vulnerability assessment tools. There are a lot of different tools out there and different ways of using them, but they all require these basic drivers. And I'll give you an example of one in a few minutes. The other thing that we can do is look at how the distribution of climate-related threats relates to non-climate-related threats, the idea being that it's pretty hard to stop climate change right now. Progress has been slow, but there are a lot of things that we can try, adaptation strategies, and many of those focus on addressing the non-climate threats. I'll give you an example of one in a moment. This also, of course, in the NPLCC's mission is dealing with those related threats. So the idea is that we can look at the distribution of all of those issues and try to get at the sensitivity, exposure, the adaptive capacity of the systems we're interested in. These being, of course, the key components of vulnerability assessment. So I wanted to give you an example of how we're doing this right now in the system that I work in, which are these amazing creatures of amphibians in the Northwest Mountains. So some of the species of concern that live in these montane areas, we have some in Washington, also Oregon, California, and several federally listed species, which are pretty much also from California. These are some of the kinds of species that we're thinking about in this part of the project. In Washington, where I work, I'm mostly focused on the Cascades frog. But if you think about these regions of, for example, the parks where we work in the Northwest, we know there are these different kinds of habitats. We know something about their hydrology and how quickly they dry up. And we know something about the ecology of species that live there that have this gradient of developmental times that relates to those different habitats. So you'd expect to find more northwestern salamanders in the permanent ponds, and you might find more cascade frogs in some of those intermediate habitats. So we can kind of line up the species life histories with the types of habitats that they use, and that influences their risk, both their exposure in terms of what are their primary habitats and how are those likely to be affected by climate change, and then what's their sensitivity based on their life history. So we can use all of these pieces that we've developed and then think about what are the non-climate factors. And in my case, one of the big ones that comes to mind are introduced fish, which were introduced very widely across the western mountains. These are mostly trout, introduced in the 40s and afterwards. And they have very strong negative effects on amphibians. So a lot of those bigger, deeper lakes where the trout have been able to persist are devoid of amphibians, and they prevent amphibians from recolonizing. So, under a scenario of climate change, that means that if you're a Cascades frog and you historically had all of these different habitats to use, now you can't use the big, deep, more climate-resistant lake, but climate change is affecting the shallower, more ephemeral habitats that they're currently relying on. They're getting squeezed between those two, and so there's a potential for, fairly rapid losses of local populations because of those two factors. But on the flip side, folks like Roland Knapp and others have demonstrated that it's actually possible to remove introduced fish from from lakes in a lot of regions, and that the amphibians really successfully recolonized. So that gives us a climate adaptation strategy for actually restoring resilience to climate in the face of climate change. And so this is something that we've been working on. It costs money, is the thing, and they're very labor intensive. And so the idea is that a lot of managers are asking, well, where do we target the effort so that you're going to get the most bang for your buck? And that gets that question of where's the risk the highest, where's the exposure the highest, and so where are the optimal places to intervene as top priorities. So we can kind of compare, what happens under these different scenarios of drying risk and the proportion of fish-free habitat that's available if we do nothing. What does that risk look like if you do fish removals from some of those sites? And this is actually happening in North Cascades National Park. We're working closely with managers and the science coordinator, Gina Rochford, there to actually apply the models that were developed and look at their fisheries management plan in light of climate change and potentially adapt that plan if it looks like there are areas that would be higher priorities for fish removals than what they've planned for under the existing plan without taking climate into account. So that's a direct application that's actually in progress right now. There are a lot of other applications, and one that isn't happening yet, but we've explored with the Washington Natural Heritage Program and Nature Serve is using our models to inform some of their climate change vulnerability indices. So, for example, this image is just the different nuts and bolts of what goes into their vulnerability index. Our maps and models would help quantify what the direct effects of climate change are, the climate stress, envelope index, the dynamic processes, and then we can use existing data that's being collected, for example, by the Natural Heritage Program to evaluate what the indirect effects and potential adaptive capacity of those systems would be, and to look at that also with respect to specific species of concern. And so what's happened historically is we've had some ecological data, but it's been pretty hard to quantify the direct effects, particularly for wetlands, and so this gives us an ability to do that. So that's something that we've been exploring with them. There are a lot of other potential applications, and I hope to hear from you all on some ideas on that. But looking forward, what we are in some cases doing now, we're planning for the future. We've already expanded our wetland monitoring. We're starting to monitor wetlands also at the lower elevations and hoping to develop projections for the Puget Sound lowlands on the west side, and also more extensive areas of the Columbia Plateau, and also working towards more focus on riparian wetlands within the Montane region. So this gets us over kind of broader areas of the Pacific Northwest. We have some preliminary results on water temperature that I didn't show in the interest of time, but that, of course, is another really key ecological driver of species use of these different habitats. And so we're looking at how water temperatures are likely to change in addition to the water volume and depth, and how that could potentially interact with things like species development times that are a huge question mark in terms of species' ability to respond to climate change. And then, of course, using all of these right now for a vulnerability assessment of amphibians in the Montane region that we're hoping to complete over the next 6 or 8 months, and then extending that to other species, such as terrestrial amphibians or other species of concern that are seeking wetlands or really responsive to things like soil moisture that we're monitoring and modeling. So with that, I want to thank my agency collaborators, a lot of people who have provided data and permits for us to do our work. Huge thanks to the North Pacific LCC for really fantastic support, especially on the front end of this project, and also for helping us to communicate our results to folks like you, and then our other funders who've been a part of the project. I'm happy to answer any questions now, or also feel free to contact me. I am responsible for the ecological applications portion of the work. If you have specific questions on hydrologic models, Lee is the best contact, and her information is there. And then for maps and remote sensing, Megan Halibisky, and I can also provide a contact to them if anyone gets in touch with me. So thanks again. Oh, that's the end of it. And I'm happy to take any questions.
Let's just go ahead and see how it works for people that have questions, just to jump in and go ahead and post your question. If there's too many people, then we'll moderate it and do it through the online system. But if you have questions, just go ahead and jump in. I've got a couple more, and I'll just throw this out there to get the conversation started. One is, I know this work really applies to the high elevation montane wetlands of your study area. Yet in Washington and Oregon, there's a lot of mid-elevation and lower elevation managed forests, or forests that go clear down to low elevation areas that are supplied more with groundwater. Where's the elevational limit by which your study design is applicable and where it's not?
Yeah, so it's a little bit different on the east and west side. So if you think about, the places that we see the largest impacts are those that are in that transitional zone that are either shifting to rain-dominated or shifting from snow to transitional. That falls, depending on where you are, on which side of the mountains at different elevations, anywhere from, 1,000 meters to 1,500 meters or so. So we think of, for the most part, our projection area is of about 750 meters. It's a little bit lower on the west side than on the east side. In some cases, our models, I think, are going to be quite useful if the ponds are structurally like the ones up in the mountains. So they're, pothole ponds. They don't have a huge groundwater component. They may have some groundwater component, but they're driven by hydrologic processes that are similar to the snow. Our projections would probably still be fairly good. Where they don't work as well so far, and what we've tested is big riparian wetlands in the lower elevations, because those just represent very different hydrologic processes. So we need a model for those. Does that make sense?
Yep, thank you. Questions from others on the line?
I have one. In some areas, as it goes terrain dominant and the possibility of flashier floods, meadow restoration is being proposed as one possible response to that. Do you think that this type of modeling could be linked to see if that would be effective, if that's going to be an effective use of restoration funds?
That's interesting. So is the objective with the meadow restoration to slow down the water and
Yes.
capture those flash floods? Yeah.
Capture the flash floods and reduce the peaks and extend the relief.
Yeah, exactly. That's interesting. So I think I don't have a super easy answer for that. And just thinking of it off the top of my head, many of the systems that we're modeling up in the mountains, so we kind of have these two different types. Some of them are like meadow wetlands, and then some are these isolated ponds. And so we do have, we have been working on those sorts of systems. So it depends on what kind, like if it's a big, a kind of large meadow with slower moving water, it's gradually going up and down with those floods, then I think we might be able to capture some of it. If it's the kind of, what we haven't worked on yet, actually a next step in the project, are things like overflow wetlands, where if you imagine there's, there's a river and then there's a large overbank event during the flood that fills those ponds, but they may be somewhat hydrologically isolated otherwise from the river flow. That's kind of a different hydrologic process. That's something we're actually hoping to work on. But I can imagine from what, from what it sounds like, I think that it would be very interesting to look at whether our models would work for that sort of a system. And off the top of my head, I think that, there would be some good chance that they would be applicable.
And will there be a link for others to be able to look at this if I wanted to forward it on and say, here's something you might want to be thinking about?
So I think, John, this webinar will be available on the NPLCC site, right?
Well, you can go to our resources page and look at past webinars, and you'll be able to see this and forward it. We're also going to put it up on our YouTube channel as well.
And I'll keep in touch with everyone at the NPLCC, and we're getting a website up, and it's not quite up and running yet, but it will have all of these resources, so the new maps, the hydrologic projections. I'm happy to share any of that if you contact me now, but also we'll have that available on the web sometime within the next couple months, and we'll keep in touch with NPLCC to provide a link to that as well, but that is forthcoming. It would be really interesting to talk more about the specifics of what those restoration projects look like, what the objectives are, and I think I could probably answer your question more effectively. And I'd want to bring Sayun in also, since she's the one who does, directly does the work on hydrologic modeling.
Mm-hmm.
This is Tom Taylor with the Corps of Engineers. And I'm wondering if you have on your site publications that address this projected effect that may be useful in effects assessments when we're looking at wetland impacts due to development and whatever reason. Are those kind of citations available?
So do you mean citations to our model or citations to other kinds of impacts of land use change?
To your publication. Are there publications yet that might be cited on your website?
Yeah, so there's one that's in review. Actually the project, the core project for the NPLCC is in review right now. We have a paper that's coming out in Frontiers in Ecology and the Environment that's an overview of all of this work, so it doesn't have new data, but it provides sort of mapped out the fish and climate change issue and then the resources that we're using, and I'd be happy to forward you that if you shoot me an email about it. Those are the two. We have several others that are in preparation on. So the object-based methods for mapping, Megan has one paper that's available on that. So there are a few resources that are available, and then others I'm hoping within the next couple months will be out in press, and I'd be happy to share them with you.
Okay, yeah, I'll send you an email. I believe I have your address, and I appreciate that. Thank you.
Yeah, of course.
Another question in the last minute or two?
I had one, and just looking at some of your slides, it seems like there's, the deeper ponds at higher elevations are going to be the ones that maintain their water during your, projected simulation out through 2080. Is there any sort of, or did you do any sort of analysis as to what the depth, might be of a pond or a water body that's going to maintain, as opposed to one that will probably, disappear during that simulation?
Yeah, so, overall, of course, the shallower pond, the more vulnerable it is drying out completely. What we're able to capture is, are the changes that are the result of the, surface level processes. So what we may miss in some cases, if there are really fundamental changes to groundwater flows, that could break some of those rules, where you might have some deeper ponds that actually have substantial effects. Because the VIC doesn't have groundwater per se, it sort of mimics it in that lower soil moisture layer, but it doesn't capture it specifically. There could be some, some anomalies, but generally the deeper ponds are the ones that that are going to be more resilient to climate change. Is that answering your question?
Yeah, that's what I was thinking. I just wondered if you guys had tried to model, just at various elevations with or without groundwater effects, what ponds, what depth, you might see that break at, where, is it 10 feet, is it 20 feet, is it 30 feet in depth that you're either going to maintain or lose, lose your sustainability of that wetland or water body.
Yeah, so I could say a little bit more on that. A lot of the sites that we're looking at, they kind of fall into a couple categories. There are the bigger, deeper ponds, and then many of our sites are less than 2 or 3 meters deep to begin with. And so some of those will, we do expect to, like many of the perennial sites that may be only 1 meter or 2 deep, I showed that one graphic showing that some of them shift to losing a lot more of their volume and drying occasionally, but many of them will actually, even just at that relatively shallow depth, the projections are that they'll hold water. It will just be much shallower and warmer, and so it might, result in some ecological changes, but it'll still be there as a pond. In terms of whether there's a specific threshold at different elevations where we are likely to see pond loss or maintenance, that's a really good question, and I would have to look back through the data through that frame to answer it, and I will do that. I think it's a great question.
All right.
But in some cases, the depth is shallower than you would expect in terms of places that will are projected to still be there. It's the really shallow ponds, the ones that are like less than a meter and a half deep, that tend to, of course, be the most vulnerable. And then those very deep sites, you really would need a groundwater model to get a better grasp on what some of the processes that we're not capturing with the VIC might be, but in terms of the VIC model, they may drop quite a bit, but are still going to be there.
All right. Thanks.
Mm-hmm.
Thank you very much, Maureen, and all the participants. It's 3 o'clock now. I think if we don't end it now, we may get turned off by our WebEx system. So thank you very much. I think the management relevance of this work is clearly apparent. We're going to do what we can on our website to make sure people can get connected to this work and the publications and future pieces. So visit our website if you are interested in following up with Maureen or contact her directly. So with that, we'll conclude this webinar and look forward to folks continuing the dialogue with us through our website or through phone calls or through email system. Visit nplcc.org if you're interested in getting a hold of us. Thanks, John. Maureen and everybody else.
Great information. Thank you.